We're going to read reverse engineering plankton write-up challenge for Google City of 2023. No, this write-up was created by a challenge tester during our internal test run. Okay. After taking a look at the binary and a decompiler, we understand the code is moving an object around a map according to some simple rules. I later learned these simple rules are how Langton moves. Awesome. Langton is like a mathematical or a simulation thing where if you get onto one color, you will move one side. If you get onto other color, you will move on the side. Eventually, it spirals up to infinity. Whatever. So, when the object reaches a point, a given endpoint, the simulation is stopped. The code that checks if the object ever passed through a specific point, which we refer to as a checkpoint. If so, we win. The map is encoded as a bitmap in binary. For starters, we can try to understand what the map looks like. Most points are initialized to 0 and some are set to 1s. Input flag toggles some points in the map based on the bits of the provided flag. To better understand the map, we generate the images of the map. The complete map is fairly large, so we generate images of top lines, the bottom lines, the area around the checkpoints, and area around the endpoint. It turns out the map looks like some sort of electric circuit. Top left corner of the map, the green dot at the starting, this one. The blue dots are position initialized to 1 in a bitmap. The red dot is a dot enabled or disabled depending on the input flag. Okay, this red one, these blue ones are what? Positions initialized to 1. The red ones might be 1 or 0 according to the flag. Bottom left corner of the map, the checkpoint is contained in the lower left fuse, which we will get to later. It will probably be useful to create a emulator so we can play the problem more easily in Python. I re-implemented the algorithm from the binary in a Python script based on some test input flag. We can now draw the path of the object. This is the path some incorrect flag. We observe some initial random moments until it touches and sticks to circuit following in generating similar images from the different input flag. Shows the path taken is slightly different, in particular different fuses light. At this point, we understood that the path taken is influenced by bits of the input flag toggling right bits. Well, make the path go through the checkpoint in the lower left fuse. Next, we need to understand the logic that determines the followed path. We recognize rows of what I will call fuses in the map. Not every position in the row contains a fuse. If a position in a row has a fuse, it can turn on depending on the path taken. Example of a turned on fuse. Example of a turned off fuse. Clearly, there is some difference. The fuses that turn on in a row depend on the layout of the circuit, which is fixed by bitmap and state the fuses in the previous row. Some of the fuse states of the first row are influenced by the input flag, while subsequent rows will influence which fuses are turned on in the last row. The input flag sets some bits which leads to an initial state of turned on fuses. Different connection between rows of fuses are possible. Fuse states can be swapped and ended, inverted, simply propagated through on or off regardless of the previous row, or duplicated. To be more precise, rows of fuses are actually separated by two layers which influence state propagation. Connectors is the fuse on the next row actually connected to the previous row. If not, its value will be independent of the previous row. Fuse with a connector to the previous row, that is, the previous row will influence its state. Fuse without a connector to the previous row, that is, its state independent of the previous row. Okay. Logic that sets the state of the fuse in the next row based on one or more fuses in the previous row. Example, swap and invert, etc. The name of these gates are invented by the Wright author. Swapper, swapper gate. Fuse states are swapped with respect to previous row. Duplicator gates. The two fuse states are duplicated from previous row. AND gates. Both fuse both fuse in the previous row has been turned on, but the fuse to turn on. Identity gate. The fuse simply is copied from the previous row to the next row. Inverter gate. The fuse state is inverted from the previous row. Now that we understood the logic behind state propagation, we can write a high-level simulator which separates a granularity of the fuse and which emulates the propagation of the fuse states based on input flag. The to achieve this, first we need to do some annoying map parsing, extract the position that contains a fuse, the position that contains connector, the position of the different gates. To verify correctness, we can test a few input flags and compare the states of fuses in the last row with those in our lower level emulator. This the only thing left to do is to translate our higher level emulator and check point conditions in a Z3 problem. Z3 is like a SAT solver, and let Z3 do the calculations. We create a matrix of a Boolean Z3 variables, one for every field. We set the top rows users to false except for the fuses controlled by the bits input flag. We end an we add an equation for every false state based on the fuse states of the previous row, the gates and the connector. We add an equation that the leftmost gate of the bottom row should be turned on at the end, the checkpoint. After the Z3 solves these containers, we extract the turn on fuses from the calculated model to obtain the distinct bits in the flag. The solver script can be found in the sol.py. The related images parsing artifacts can be found in the artifact directory node. After solving the challenge, I learned it's inspired by this paper, in which the terminology of gate names is slightly different. Yeah, this is the thing I said. Goes to infinity. Draw, parse, simulate.